Hello, this is my lab report for Lab 2, Motion of a Falling Object. So, like the title suggests, this lab focuses on the motion of a falling object. It involves gravity, drag, and terminal velocity. For our model, we will use the position update formula and Newton's second law. For our model, there is a force of gravity causing our object to move down in the negative y direction, and there is a force of drag opposing that motion. In order to calculate the velocity and position of our object, we will be using the position update formula from Newton's second law. And we will use the final velocity instead of the average velocity because our force is not constant. In our computational model that included the drag force, we found that given enough time, we would eventually reach a state of dynamic equilibrium, where the force due to drag and the force due to gravity would cancel each other out. In our real-world experiment, we were approaching terminal velocity. Our assumption is that the drag force is proportional to the square of the object speed. Positive y is up, negative y is down. Acceleration due to gravity is 9.8 meters per second squared, and there are no forces acting on our system other than gravity and air resistance. For the experiment, we found an object that could fall straight down but also experience some drag force. For us, this was a crumpled up piece of paper. And then we held it up and we dropped it from rest, and then we got the video and analyzed the data using Tracker. Our system is a crumpled up piece of paper, and the surrounding is the earth and the air. Our initial conditions are when we let go of the object, so that is time, position, and velocity all equal to 0. Here's a video of our analysis in Tracker. In our computational model, we first set our initial conditions and our b-value. The b-value for my model is 0.82. If we were not including any drag force, it would be 0. And then our ball's velocity is always going to be negative, so our drag force will be in the positive y direction. And then we calculate our net acceleration from our net force, and then we update our velocity using that information, and then we update our position using the velocity, and then we step to the next time. Now onto the data. We found that our simulation that only included the force of gravity was quite different from our observed results, because in the simulation there's only the force of gravity, which means our net force is constant and that we are constantly accelerating. Our second model better fit with our observed results. This is because in the real world, there is more than just the force of gravity acting upon our object. There is also air resistance, which decreases the magnitude of the net force as our velocity increases. Our model was able to account for this by including a drag force, and that's why it fit better. There may be some potential sources of error. The video was taken at a slight angle. There may have been human error while dropping the object. There may have been human error while analyzing the video. And also, our object was irregularly shaped. It was just a crumpled up ball of paper. This means the drag may have been different depending on how it was oriented. So as you can see on the graph, if we only have gravity, then the velocity will just keep on decreasing. However, if we include drag, then we will decrease until we reach a certain point at which our velocity will become constant. This means we have reached terminal velocity because we are not accelerating, so we have a net force of 0. So the red line has us just dropping it from rest, and the blue line has us throwing it down. At the end, they both flatten out to the same velocity. This means that terminal velocity is the same regardless of our initial conditions. The blue line where we threw it down just happened to reach it a little bit faster. Overall, we found that a state of dynamic equilibrium, which is terminal velocity, can only be achieved when we account for a drag force. The initial conditions do not change what our terminal velocity is. Given enough time, as long as the object has the same drag coefficient, we will eventually reach the same terminal velocity. And finally, while we are on the surface of the Earth, we must account for gravity and a drag force if we are predicting the motion of a falling object.